Hello, and welcome to another IoT Central webinar. I'm David O'Hara, and I'm the Managing Director at IoT Central. I'd like to start by thanking SECO for sponsoring today's event. Today's webinar is a product overview entitled Extract Data and Value from Your Field Devices with Astarte, the FOSS IoT orchestration platform. Now I'd like to introduce today's speaker. Giulio Malatesta is the Technical Marketing Specialist at SECO. Giulio, when you're ready, let's get started.
Thank you, David. Hello, everyone, and welcome to this new webinar. My name is Giulio Malatesta, and I have been contributing to SECO's activities for 5 years in various commercial and technical roles that allowed me to realize the effort that OEM manufacturers, system integrators, and cloud solution providers put into finding ways to easily offer services based on IoT data on the market, thereby adding value to the entire value chain of manufacturing of physical goods. And at the same time, they unlock new and more profitable business models with a data-driven approach. And in this productive context, SECO has created Clea, the software suite which allows complete management of devices, data, and applications in an IoT project. Clea includes Edgelog, an IoT fleet and device orchestration platform. Clea Portal, a dashboard that allows data consumption through custom graphic applications integrable with a click, and notably Astarte, which manages data orchestration and constitutes the foundations of the whole suite. So today, I'll guide you through Astarte's design concepts, development approach, and a practical use case scenario to demonstrate what we'll discuss. Let's now dive deep into it. So Astarte is a free open source platform which is designed for data orchestration within IoT context. It handles and processes IoT data and context data from collection to processing, qualification, storage, and retrieval. And Astarte simplifies the complexity and learning curve to maximize data utility, offering a robust ecosystem to connect devices and manage data flows in real time, ensuring interoperability and scalability. It employs open technologies and frameworks like MQTT, Go, and Elixir on the Erlang virtual machine, which is used, among others, by WhatsApp to ensure extreme concurrency. Through a flexible data model and intuitive APIs, Astarte enables developers to create efficient and customized IoT applications using the collection, aggregation, and analysis of IoT data on a large scale. With support for integration with other applications and the ability to manage millions of simultaneous connections, Astarte is ideal for companies looking to leverage IoT data to enhance operational and strategic decisions. Now, let's dive deeper into Astarte. Astarte is a native Kubernetes application that abstracts its complexities by facilitating the management of IoT applications on a large scale, hiding the most complex aspects of Kubernetes from developers. Kubernetes is used as the underlying platform to orchestrate the containers in which the various components of Astarte run, leveraging its capabilities for deployment automation, scalability, and failover management. This way, Astarte allows developers to focus on developing IoT-based services without having to directly manage the infrastructure complexity. Astarte integrates several key design concepts to provide a robust and scalable solution. Let's go through a detailed overview of these concepts. The first one I would say is multi-tenancy. Astarte is designed to support multiple tenants, which can correspond to customers or projects, for example, in an isolated and secure manner within the same instance, thus allowing efficient resource management and better data separation. This is essential for companies managing multiple customers or projects on a single Astarte installation. Realms are logical domains used to isolate and manage groups of devices and data within Astarte. And each realm represents a separate environment, providing specific control and security, facilitating the management of devices and data for different projects or clients under the same tenant, of course. The system ensures effective separation of resource and data, which is critical for privacy and security in multi-tenant environments. Moving on to interfaces, which is another key concept in Astarte. In Astarte, they define data models for communication between devices and the platform, and vice versa. They allow flexible configuration of exchanged data types and are essential for ensuring compatibility between different device versions. Each interface is essentially a JSON, also modifiable in a GUI fashion through the Astarte dashboard, which defines how data is exchanged between devices and the platform. There are two main types: property interfaces which are used for data that does not change frequently, such as configurations or stable device states. And then data stream interface, which are designed for data that changes dynamically and frequently, such as real-time sensor readings. Interfaces can handle various data types, such as booleans, integers, decimals, strings, binaries, support complex formats like arrays and objects. And each interface can be versioned to handle backwards compatible changes, thus facilitating device and application upgrades without interruptions. The versioning system mimics a semantic versioning model where major changes require a new major version while incremental additions are reflected in a new minor version. Interface aggregation allows treating multiple related data as a single object, ensuring logical organization that reflects the physical structure of the devices and or their components. This structuring facilitates the platform's adaptability to an endless range of use cases through targeted and precise initial configuration of the data model, which you're kind of forced to. Another useful concept in Astarte is a trigger, and triggers allow for the definition of automated actions based on specific events, such as surpassing a data threshold. Say, for example, the temperature of a room goes above or below a given threshold, or a consumption app posts some specific data on an interface endpoint. This can be configured through the Astarte dashboard, Astarte CTL, or via API, and are crucial for process automation, of course. So using a JSON to define condition and action, conditions can be based on data or device states, triggering actions such as an HTTP request to specify the URLs when data meets certain criteria. Triggers support multiple types of actions and configurations, and they offer flexibility and integration with external services. But how is data handled in Astarte? Well, the Astarte MQTT version 1 protocol is an advanced version of the MQTT version 3.1.1, and it's tailored to maximize Astarte-specific functionalities. It supports efficient and secure communication, facilitating the transmission of data and commands between devices and the platform. And this protocol does not impose a data serialization format, allowing developers to choose or define their own, but it provides one for comfort. Astarte uses Bison for serialization, optimizing bandwidth usage and ensuring orderly and asynchronous transmission. This protocol facilitates efficient and flexible communication between devices in the Astarte platform, supporting a wide range of IoT use cases without tying users to a single transport format. But let's now dive deeper into how the pairing mechanism in Astarte plays a crucial role in ensuring that only authenticated and authorized devices can interact with the platform. This process involves several key steps to ensure data security and integrity. To begin pairing, a device must first be registered within the Astarte platform. And this includes creating a unique identifier for the device and associating it with a specific tenant, and optionally with a group of devices within that tenant. During the registration process, specific credentials are generated for the device, and these may include SSL certificates, secret keys, or other authentication methods that the device will use to establish a secure connection with Astarte. When the device attempts to connect to Astarte, it uses its credentials to authenticate itself. And the platform then verifies these credentials and, if valid, authorizes the device to send and receive data. This process ensures that only devices with valid credentials and properly registered can access Astarte services. And so the pairing system also manages the life cycle of device connections, including credential renewal, access revocation in case of compromised devices, and updating security policies. This is a layered approach to pairing that not only enhances the overall security of the platform, but also offers flexibility in managing devices on a large scale, essential for IoT applications in dynamic and variable environments. The pairing mechanism in Astarte uses various standards to industry standards to ensure a high level of security in cryptography and authentication during the device pairing process. Technologies such as TLS and SSL ensure that all communications between devices and the platform are encrypted and secure. JWTs, that is JSON Web Tokens, are used for authentication, providing a standard way to issue secure information exchange between parties on a network. This approach allows scalable, secure scalability for large-scale IoT applications, enabling administrators to easily manage large numbers of devices without compromising security. As for user interactions in Astarte, it differs from traditional login concepts as known in web or mobile applications. Instead, Astarte manages access and security primarily through authentication and authorization mechanisms, the ones that I've just mentioned, basically. And for users, you might ask, for users administering the platform following the IoT security model, access is managed through Astarte's user interfaces, so both GUI and CLI, or through the APIs by providing an authentication token, which can then be customized as to which features are readable or writable by the authenticating users and the token lifespan. As for the tools and methods for interacting with the platform, each suits different needs and usage scenarios. Here is how the dashboard, Astarte CTL, and REST APIs work in detail. Let's start from the Astarte dashboard. It is a web graphical interface that allows users to easily manage and monitor the Astarte platform. Through the dashboard, users can register new devices, view the status of existing devices, and manage their configurations. It's also possible to interact with interfaces and triggers. It's also possible to create and modify the definitions of interfaces that define how data is exchanged between devices and the platform, and triggers that fire up HTTP requests in response to a specific event received or generated by Astarte devices or data consumption apps, as we said earlier. The dashboard provides visualization of system events and device metrics, useful for analysis and troubleshooting. And with this, you can also manage access permissions to various parts of the platform by creating custom authentication tokens. Instead, Astarte CTL is a command line tool that offers users a powerful and flexible way to interact with Astarte. With Astarte CTL, users can automate operations, and the tool is ideal for automating repetitive tasks for integration with other CIs, CTC systems. It can be used to run complex scripts that facilitate the deployment and maintenance of Astarte production. In a similar fashion to the dashboard, but from the command line, users can install interfaces and triggers and all necessary operations for device and interface control. Lastly, REST APIs allow developers to fully integrate the platform with third-party applications or to build custom applications that leverage Astarte's capabilities. The APIs offer maximum flexibility to developers who can use them to access all aspects of Astarte, from device management to data queries to sending commands to devices. REST APIs enable integration with any data consumption application, such as data analysis and qualification platforms or enterprise applications in general. The APIs are essential for writing scripts or applications that automate complex operations or require programmatic interaction. So in summary, Astarte offers versatile tools for different types of users, from visual and intuitive management with the Astarte dashboard to the flexibility and power of Astarte CTL and REST APIs for developers and system engineers. These tools enable smooth management of data flow between IoT devices on a very large scale. But now onto the database management system of Astarte, which is designed to be extremely scalable and performant. It supports the storage of large volumes of IoT data and the efficient processing of complex queries. Astarte utilizes Cassandra or ScyllaDB to store all data. Each tenant of Astarte, known as Realm, has its own key space in Cassandra, which can be configured according to specific needs. So the system automatically handles the creation of key spaces and tables and manages migrations between versions. Cassandra and ScyllaDB are both distributed databases designed to offer high scalability and optimal performance on a large scale. Cassandra excels in handling large volumes of data with fast writes, geographical distribution, and easy horizontal scalability, ensuring high availability and fault tolerance. But ScyllaDB, compatible with Cassandra's API, is known for its efficiency in utilizing hardware resources, providing lower latencies and higher throughput due to its optimized architecture and non-blocking threading model. So for this reason, for example, companies like Netflix, which require high performance and quick response times to manage large volumes of data efficiently, employ ScyllaDB. Both support seamless scalability and are suitable for applications requiring high performance and large amounts of data. So let's talk about scalability. In the complex world of IoT, scaling features and reliability are paramount. Astarte stands out by integrating advanced technologies and architectural choices to ensure both. At the heart of Astarte's message handling capabilities lies VNMQ, a well-trusted MQTT broker enhanced by the Astarte VNMQ plugin, which enriches incoming MQTT messages with metadata and publishes them on an AMQP exchange for further processing. This setup is complemented by RabbitMQ, which is employed as a robust reply queue mechanism, ensuring data resilience and integrity. Astarte harnesses the power of Elixir, which is a dynamic functional language designed for building scalable and maintainable applications. It's built on the Erlang VM, which is called Beam, and it's known for its prowess in developing distributed fault-tolerant systems, and it enables Astarte to treat all features as microservices. This architectural decision guarantees that the failure of an individual component does not impact overall system performance, mirroring the reliability seen in massively scalable systems like Meta's WhatsApp. Key to Astarte's performance is the data plant, or DUP, a dedicated microservice for data ingestion that employs a sophisticated scaling strategy. So DUP utilizes Erlang's lightweight processes, assigning each connected device to its own process. This ensures that messages from a specific device are processed consistently and in the order of the transport ingestion, which is a critical design choice for maintaining data integrity. And to manage high data throughput, DUP leverages both horizontal and vertical scaling. Horizontally, it expands capacity by adding more instances, with each with its dedicated set of RabbitMQ queues. This not only distributes the load effectively, but also minimizes the impact of potential bottlenecks. Vertically, DUP can enhance its processing power by utilizing additional computing resources, allowing the Erlang runtime to distribute workloads more efficiently across available resources. In environments where massive throughput is required, DUP's approach to message sharding across multiple queues significantly optimizes performance. Whether scaling up or out, Astarte's infrastructure is designed to handle vast amounts of data without sacrificing speed or reliability, making it an ideal platform for enterprises requiring robust IoT solutions. We should certainly discuss Astarte's approach as free and open source software, FOSS, which offers significant advantages for businesses. So being FOSS means that Astarte is transparent and accessible, allowing users to verify and modify the code according to their needs, thanks to the extremely liberal licenses, such as MIT and Apache 2. This reduces the risk of lock-in with a single vendor, a common concern with proprietary software. So companies and individuals can adapt the platform to their needs without depending on a specific provider. They can change its brand, resell it as their own, even without mentioning SECO. This openness ensures that solutions are secure, reliable, and aligned with the industry standards essential when handling possibly sensitive data. Astarte's FOSS approach demonstrates a significant focus on developers, the main users of the platform. SECO, by supporting Astarte, commits to providing a detailed and clear online documentation, well-documented public code and repositories, and a transparent and open process for contributing to the project. This welcoming and collaborative environment allows developers to easily integrate into the community, solve problems, and innovate, feeling an integral part of the development and improvement of the platform. And we look forward to seeing you on GitHub. Find us on @Astarte-platform. From another perspective, SECO is well aware that not all entities and individuals interested in building an IoT offering in the market have the capabilities or even just resources to set up and maintain an IoT infrastructure, especially after the POC phase. When going into production, they face the challenges of devices installed in the field, a real field, and they're used by users, real users. The need for on-demand scale-up, as well as the reliability of the infrastructure, are key factors to consider. For this reason, thanks to the partnership between Google and SECO, we have made Astarte available as the first component of the Clea suite that can be downloaded and installed in your own Kubernetes environment with one click from the Google Cloud Marketplace. Similarly, Edge, Clea Portal, and the rest of the suite will soon be available on GCP. Just like on-premises installations, it will be possible to cherry-pick the components that provide features missing from the customer's current IoT infrastructure, or use the entire suite as a turnkey solution to provide value-added services to the end users of the platform and data consumption hubs. Let's now explore a real use case scenario in the healthcare field. So medical devices, for example, are notoriously expensive and constitute a significant barrier to market entry. Especially in areas where diagnostic and therapeutic activities are carried out exclusively through specific machinery. So, for example, consider dental care. Many doctors must necessarily associate together to reduce the cost of purchasing and amortizing these assets. A real-world use case of one of our clients currently in production involves medical and veterinary machines that perform laser treatments on skin or dental therapies. These machines, normally very costly, can instead be offered on the market on a free, loan-for-use basis, in addition to which a maintenance and replacement service for the machinery can be purchased in case of fault. The machine provides laser therapies because it has been connected to the internet at least once and has communicated with Astarte at least once, which acts as the data orchestrator between the devices and third-party applications. Thus, the doctor can purchase credits directly from the machine screen on an online platform. These credits will correspond to seconds of therapy delivery. In this case, Astarte takes care of orchestrating all the data of the infrastructure services, which collaborate to provide the service to the end user. It is responsible for authenticating and authorizing communication between the machinery and the cloud, and enabling the machine's registration features on the platform and its association with the user, who is also authenticated, allowing them to purchase the therapy credits on a dedicated web portal, which was custom designed and integrated by technological partners of our clients without our help, thanks to the extended available documentation. This radically changes the business model, because most of the margin now comes from the therapy credits business, constituting a stable and predictable cash flow for the company, which can thus better plan and dedicate itself entirely to developing what it does best, its laser therapy technology. The doctor is not forced to associate with anyone to default the cost of the asset, which is instead accessible for free, and is aware that the only cost parameter will be the price of the credits to deliver the therapies. Thus, the risk that the asset breaks down suddenly and requires repairs, interrupting the service, disappears, as do the costs of amortizing the asset and the concerns arising from its normal wear and tear with use. Stay tuned for news on Clea as its development moves forward on GitHub. Join SECO's mission to create technologies to shape a better future. Visit seco.com for more information. And now let me turn it back to you, David. Ciao.
This brings our webinar to a close. I'd like to thank Giulio for his insights, and thank you to SECO for sponsoring today's events. You can view more webinars at iotcentral.io. Thanks for watching.